let's explore the development of sex differentiation in the gonads, the ovaries, and the testes, and also in the external genitalia. We should get some terminology settled first, though. We've already talked about chromosomal or genetic sex. This refers to the genotype of the sex chromosomes. Is it XX, XY, X, XXY, XYY, etc.? Then there's reproductive anatomy. Reproductive anatomy is determined by chromosomes and hormones, and also these days by surgery. Gender identity is a person's inner sense of being a man or a woman, both or neither, and it may or may not correspond to external characteristics. And then there is gender expression. This is the outward expression of one's gender identity. We are now going to focus on the sex differentiation that happens during the first trimester of gestation, that early stage of pregnancy, when the ovaries or testes are formed, and also when the external genitalia starts to form as well. Embryonic development it unfolds in exactly the same way for the first 6 weeks after fertilization, post-fertilization. At week 6, they begin to differentiate into male and female. So males and females, they start with the same genitalia and then they differentiate. So this means that men and women, male and female bodies, are made of homologous parts, so developmentally. So this starts with the development of the primordial genital ridge. There are 6 genes that are involved with the development of the primordial genital ridge. Then you have week 6 happen, and you divide it then proceeds along a masculinization trajectory or its default trajectory, which is the feminization. So you have the development of ovaries or the development of testes. There are 4 genes involved in the process of ovary development, and there are 5 genes involved in the development of the testes. Then the external genitalia form. There are 9 genes involved in the development of the uterus, the fallopian tubes, and the vagina. And there are 14 genes involved in the development of the testes, the seminiferous tubules, and the prostate. So if these anatomical terms are kind of new to you or you've forgotten what they mean, don't worry, we're going to get to them in a later video, I promise. So, and then you have, the next stage then with the external genitalia forming. One of the things I want to point out is that as we look at those, that ever since 6 weeks when they have divided into forming ovaries or testes, and then forming the external genitalia from there, is that only two genes are shared between these 2 processes. Only 2 of them are in common. So in total, there are 37 proteins and 2 hormones involved in the development of the genitalia. So if we add up all of those genes that I mentioned in the previous slide, 37 proteins and 2 hormones involved in the development of the genitalia. If we let each of these proteins be expressed in just 3 ways, so high, medium, and low, which we know that there's many more options than that, but let's just, for simplicity's sake, say that there's just 3 ways that they can be expressed. Then there are 3 to the 37th amount of possibilities of combinations, or 450 quadrillion combinations. What that means is that there is a lot of room for variation. A lot of room for variation in how the gonads and the external genitalia form and what they look like. So now back in Module 3, we talked a lot about variation and how variation is distributed. Some phenotypes have a unimodal distribution, and sometimes variation has a bimodal distribution. When we see a bimodal distribution within the phenotypic variation that we're investigating, biologists will often start to ask whether or not the phenotype, or whether the morphology that we're looking at, is sexually dimorphic. Does it differ between males and females? Now, we have seen that sexual dimorphism, we have seen this pattern happen with height. We've seen sexual dimorphism in weight, dimorphism in the shape of the chin, the brow ridges, etc. You've even seen human sexual dimorphism in height. Remember that in all of these, there's also an awful lot of variation. So in the height of this group of students, there is sexual dimorphism, but there is so much overlap in height in this population that it's not actually bimodal. So bimodal can be pretty differentiated, or a tremendous amount of overlap to the point where your dimorphism actually isn't bimodal, if you're following me. Now, when it comes to genitalia and gender identity and gender expression, variation is more bimodal than height. But because of how many different genes and hormones and environmental influences there are on the development of these sex phenotypes, there is overlap. The sexual dimorphism of human genitalia and gender isn't complete. So we are going to talk about males and females, and we are going to talk about the overlap between the distribution. In the next video, we'll focus on typical male and female anatomies, and in a subsequent video, we'll talk about the intersex phenotypes.